In the next problem, we have two objects A and B that are connected by a rope and A is on a frictionless surface. The system is released from rest and A starts to move to the right and B starts to move downwards. So let's put that in as the directions of our acceleration. So A to the right and B accelerates down. We're asked to figure out what is the tension in the cord that connects A and B. To solve this, let's draw a free body diagram for each of our objects. For A, we have force of gravity down, normal force up, and force of tension to the right. For B, we have a force of gravity acting downwards, tension force acting upwards, and because the same string connects A and B and the pulley has no mass so we can ignore it, the tension acting on A is exactly equal to the tension that's acting on B. Keeping that in mind, let's now go ahead and write Newton's second law based on our pictures for each of the objects. I'm not interested in the vertical direction for A to solve this problem, so I'll just write Newton's second law for A in the x direction. The only force in the x direction on A is the tension force, and that's going to be equal to the mass of A times the acceleration. For object B, we have a tension force pointing upwards, force due to gravity, acting downwards, and because B is accelerating down, I need to add in a minus sign for the acceleration. For the same reason why the tension force is the same for both of our blocks, the acceleration is the same as well. They move as one unit, B pulls A, and the whole system moves to the right for A and down for B. At this point, we now have a two-equation, two unknown problem. So what I could do is solve this equation for A, plug it in over here, and then solve for Ft. So doing that, I have A is equal to Ft divided by Ma, plugging that in over here, now I have to solve for Ft by getting it all on one side. So I'll move all of my Ft terms to the left-hand side. And move this term to the right-hand side. I can factor out Ft, and then divide to get Ft by itself. Plugging in the numbers, MB is 40 kilograms. And MA is 29. So that if I put all of this into a calculator, I would end up with a force of 164.8 newtons, which rounds to 165. In this last problem, we have a person pushing a box up a hill. And the important thing here is that the box starts and ends at rest. And as they're pushing it up the hill, we want to figure out how much work do they do in that motion. To solve this, we'll use the work energy theorem, which says that the net work is equal to the change in kinetic energy. This is why the fact that the object begins and ends at rest is important, because if I were to calculate its kinetic energy, I'd have 1/2 m times 0 squared for the final velocity, minus 1/2 m, with the 0 as my initial velocity for ki, and this whole thing is therefore going to be equal to 0. For my left-hand side, I need to figure out the net work that is done on the box. So if I just look at the box as it's being moved up the hill, and specifically focus on the forces on it, I have a force due to gravity, normal force, the force from the person, and there's also a friction force that's present as well. My direction of motion is up the hill, which means that the force done by the person, the force due to gravity, and the component of the force done by friction, and the component of the force due to gravity that's along the incline all will do non-zero work on the box. The normal force and the vertical component of gravity will do no work on the box because they're perpendicular to the displacement. And so we can therefore end up calculating all of this as follows. So my left-hand side will be the work from the person, which is what I want to solve for, plus the work done by friction, plus the work done by gravity. The task is to now calculate the work done by friction, work done by gravity, and use those to solve for the work done by the person. For the work done by friction, this is going to be the force of friction times the displacement, and we'll call that d for right now and come back to it, times cosine of the angle between the vectors of friction and displacement, which point in opposite directions, so that's going to be 180 degrees, and will ultimately be a -1. For the work done by gravity, we can calculate this as the negative change in gravitational potential energy. So continuing on, we have work person minus mu k times the normal force on the box. The normal force on the box is equal to this component of gravity, which I'm drawing in pink. And remembering that if this is theta, this is theta, this pink component of gravity that I've drawn is going to be equal to mg cosine of theta. So we have back to our equation over here, mu k times mg cosine theta for the force. And now for d, we need a little bit of trigonometry, where if I calculate this distance here, d, and I know theta, and I know h, the height of the hill, I can figure out this as opposite over hypotenuse is equal to sine theta. So if I have sine theta equals h over d, d is therefore equal to h sine theta. And now for the work done by gravity, that's just going to be equal to negative m g times h. And now for the displacement d, that's actually what's given to us in the problem, where they tell us that if we were to think of the incline as a triangle with an angle of 30 degrees for theta, the hypotenuse d is equal to 5. So we'll just leave that as d. For the negative change in gravitational potential energy, that's going to be equal to our potential energy at the top of the hill, call that mgh, minus the potential energy of gravity at the bottom, which would be 0. H is the height above the ground, which on our triangle would be here, and we can solve for h in terms of theta and d using sine, where sine theta is equal to opposite over hypotenuse, and therefore h is equal to d sine theta. So now putting all of this together, I have the work done by the person, and I'm going to move everything that's negative to the right-hand side now, is equal to mu k mg cosine theta times d plus mg, and for h, I can use that d sine theta we just solved for. At this point, I'm in a position to where I can plug in numbers and solve. Mu k is 0.4. The mass of the object is 12 kilograms. The angle is 30 degrees. The displacement is 5 meters. And plugging all of this into a calculator, if we were to round, we'd end up with a positive 498 joules.